The best place to start in calculating the pH of a salt solution is to determine what cation and anion the salt is composed of. So let's start by writing a dissociation reaction for the sodium acetate salt. Now remember, these are always going to be aqueous solutions in our case. We really should be a little bit more clear about that in the problem stem, but it's fine for you to assume that we're dealing with aqueous solutions. So our sodium acetate is going to dissociate into Na plus and the acetate ion CH3COO minus. From this point, there's a couple of ways to approach this problem. A lot of people would have you refer to some of the tables that are in the textbook, for example, table 12.8 and table 12.9, to look at the acidic and basic character of common ions. My approach is a little bit different. I like to take a little bit more logical approach because I don't like to memorize tables. I realize you have a crib sheet, but just from a pedagogical standpoint, I prefer to reason my way through this. So what I always think about is the fact that, as we've discussed, a salt is composed, or a salt is formed when we react an acid with a base. So I want to think about what acid and what base would have been used to form this salt. The cation in a scenario like this will always be the thing that came from a base. So if we think about what base we could make using a sodium cation, what I come up with is sodium hydroxide. Now the anion will always have come from the acid, and that's a little bit easier because all we really have to do to figure out what acid that was is put a proton back on. And so we have HCH3COO, which you may more commonly see written as CH3COOH. That's the carboxylic acid acetic acid. So our sodium ion came from sodium hydroxide. Now remember, from our list of strong acids and strong bases, sodium hydroxide is a strong base. That means that Na plus is a very, very, very weak acid. So weak, in fact, that water is actually a better acid than sodium plus. If you look in table 12.8, it actually will list sodium plus as a neutral cation, meaning that it's too weak an acid to force water to act like a base. So it's not going to impact the pH of our system. Okay, let's move on to the acetate ion. The acetate ion comes from, again, acetic acid, which is not on our list of strong acids. By default, it's a weak acid. That means that the conjugate base, the acetate ion, is a strong enough. It's not strong as in on the list of strong bases, but it is a strong enough base to impact the pH of an aqueous system. In other words, it's a stronger base than water is. So it's going to force water to act as an acid. So the next step is to write the equation that shows the acetate ion acting as a base with water as its acid. If water is the acid, it's going to donate a proton. When it donates a proton to the acetate ion, we form again that acetic acid. And more importantly, we're left with hydroxide ion. Now that's important because if we think about the acid and the base that we used, what we really have done here is we had strong base with weak acid, and we can kind of memorize our way through the fact that that's going to give us a basic salt. It's okay to memorize that as long as you understand that the formation of this hydroxide ion is your confirmation of the fact that the salt will be basic. It's the production of that hydroxide ion via protonation of this weak base that makes the system basic. At this point, we can use this equation as the basis of an ice table. We always ignore that water because it's a liquid and won't be included in an equilibrium expression. And because of our 1-to-1 mole ratio, the initial concentration of the acetate ion is actually equivalent to the initial concentration of the sodium acetate. So we'll put in 0.15 molar for our initial concentration of sodium acetate. And as with all of these these weak acid, weak base problems, because at this point we really are just calculating the pH of the weak base, CH3COO-. We define initial to mean before any dissociation occurs, or any protonation occurs, and so we'll make those values of the initial values of the products 0. As with any calculation of the pH of a weak acid or a weak base, we're going to have minus X for our reactant. The reaction has to be going in the forward direction because we define those initial concentrations of products to be 0. And the one-to-one stoichiometry gives us plus X as the change in concentration for both of our products. So at equilibrium, we have initial plus change is equal to equilibrium. We have 0.15 minus X for the acetate ion, X, and X for our two products. At this point, we are ready to solve for the hydroxide ion concentration, but you have to be a little bit careful. Notice that the Ka for acetic acid was given. We're not dealing with acetic acid anymore. We're dealing with the acetate ion. So we actually need the Kb for the acetate ion. And we can derive that using Kw equals Ka times Kb for a conjugate acid-base pair. So the Kb for the acetate ion is actually going to be equal to Kw, or 1 times 10 to the negative 14th, since no alternative temperature was given, divided by the 1.8 times 10 to the negative 5th that was given for the Ka. That's going to give us a Kb of 5.6 times 10 to the negative 10. That's a huge place to look out for making mistakes when you're working these problems, using the wrong value for that Ka. Remember, this is a base, and so we must be using a Kb. The other way to think about it is we're producing hydroxide, so we must be using a Kb. So that Kb is equal to the concentration of the acetic acid times the concentration of the hydroxide ion over the concentration of the acetate ion, all at equilibrium, which simplifies to x squared over 0.15. The value of this Kb is so small that I know I'm going to be able to ignore this minus x term. I'll check it for verification at the end, but I can tell by the small value of the Kb that I'm going to be able to get away with that. When I solve for x, remember that X is the hydroxide ion concentration at equilibrium, and in this particular case, that is equal to 9.2 times 10 to the negative 6. So I can calculate my POH as negative log of 9.2 times 10 to the negative 6, or 5.04. And I'm running out of room, so I apologize, but I'm going to zoom up to the top left-hand corner. pH is then equal to 14 minus the POH, and we end up with a pH of 8.96. Again, be really careful there. It's easy to forget and stop at POH, but you want to check your logic. This is a basic solution. We said it was a basic salt. The pH should not be less than 7, so remind yourself of that. In the interest of not ending up with a 15-minute long video, I'm only going to walk you through the setup of this next problem and leave you to do the math on your own. So let's start in the exact same place. Let's look at the dissociation of the salt and figure out what cation and anion we're dealing with. NH4Cl aqueous dissociates into NH4 plus and Cl minus. Okay, let's think about the origin. Remember, the anion is always originating from the base. The anion originates from the acid. And so to figure out the conjugate acid, we're going to add a proton, and we have HCl, which is on our list of strong acids, which means Cl minus is too weak a conjugate base, or too weak a base in general, to impact the pH of water. Or you could look at one of the tables, 12.8 or 12.9, and see that Cl minus is listed as a neutral anion. Our cation comes from the acid. This one's not quite as straightforward to see, but think about conjugate acid-base pairs. Remove a proton, and we get ammonia. Ammonia is a weak base, which means that NH4 plus is a strong enough acid to impact the pH of water. So we need to show ammonium ion acting as an acid with water as its base. If water is the base, it's going to accept a proton, forming H3O+. Key difference between this one and the previous one, previous example, and leaving behind NH3. Okay, let's check our logic quickly. We have formed hydronium ion. That means this is an acidic solution. Let's think about whether that makes sense. We have formed this acid using a strong acid and a weak base, and again, helping us kind of reason our way through this, we've memorized that that will result in an acidic solution. So now you're ready to use your ice table. Be careful. Think about whether you want to be using a Ka or a Kb. Be very, very, very careful with that particular part of this, and I will go ahead and tell you that the pH in this case, after you do all of the math, should come out to be 5.04. Okay, so test yourself, make sure you can get to that value, and combine CME if you can't. We'll also work more of these in class. Always keep in mind that salts that are formed from a strong acid and a weak base will be acidic. Salts that are formed from a strong base and a weak acid will be basic. Keep in mind, though, it's actually the result of the conjugates of the weak components. In the first scenario that I described, it's the conjugate acid of the weak base that actually reacts with water and produces hydronium ion to make the system acidic. In the second scenario, it's the conjugate base of the weak acid that reacts with water to make the system basic.